In this example, I'm going to show you the application of the theory that I just talked about. We have surface AB that is a circular arc with a radius of 2 meters. Perfect. And a width of 1 meter into the paper. So it is important to notice that this is a 3D gate or surface, and we have 1 meter into the paper. Just to make sure that you get this, you understand the physics of it, this is our surface AB. This is our gate with the radius of 2 meters. And you can see how it goes into the paper for 1 meter, and I have shown you a perspective drawing, a perspective 3D drawing of the same photo that your book has provided for you. The distance EB is 4 meter, the fluid above surface AB is water, and the atmospheric pressure prevails on the free surface of water and on the bottom side of surface AB. What we're going to find is the magnitude and location of hydrostatic force acting on surface AB. All right, before we get started, just to avoid any confusion regarding notations, your book has indicated this F as FV. We are going to call this F. Let's call it F to avoid any confusion. All right, now first of all, I want you to take a look at this perspective drawing and familiarize yourself with the physics of the problem, with the geometry of the problem. So we have a circular arc that goes 1 meters into the paper, and you can see the surface of water. I have shown the surface of water with the blue lines on top of that arc. Now, the first thing that we are going to do is to find FH. FH is the horizontal force, right? Horizontal force, as I said, acts on vertically projected area of the curved surface. So vertically projected area of the curved surface would be this area. Now, so this is on the 2D drawing. On 3D drawing, the vertically projected area would be the area inside the green rectangle that I'm drawing right now. So FH acts on this vertically projected area. Okay, so if I write the equation for horizontal force, it is gamma of W H bar times vertically projected area of the curve. Now, let's plug in the numbers. H bar is the depth from the surface of water to the centroid of vertically projected area. So our vertically projected area is a rectangle. In other words, the centroid would be right in the median of the side of the rectangle, right? So to find out H bar, I can tell that this would be my H bar. And since the radius of this quadrant is equal to 2 meters, meaning that this is 2 meters, then this distance over here is 1 meter, right? Okay, so H bar then would be equal to 4 meters, which is the distance from E to B, and from B to centroid of the green line, which is 1 meter, times area of vertically projected surface. So area of vertically projected surface is simply this area over here, which is the area of a rectangle, and is equal to 1 times 2. 1 is this number over here, and 2 is the radius of the quadrant over here. Perfect. When you calculate this, your horizontal force would be 98,100 Newton, or 98.1 kilonewton. All right, so this is our horizontal force. Now we are going to calculate our vertical force. I'm going to actually show you this using two different methods. Method number one is the method that your book has done it. So I'm going to write method number one based on textbook. Your textbook says that vertical force, or FV, is equal to F plus W. Now, F is the force due to pressure on this surface, CB. And W is the weight of water right on top of AB. Okay? So now to calculate F, F is force as a result of pressure on CB. But area of CB, right? So in order to calculate ACB, you need to calculate the area of this rectangular area that I'm going over with the purple pen. This area. This area is area of CB. Perfect. How about pressure though? Pressure is easy because that purple plane is horizontal. Pressure changes only with one depth. So I can simply write that pressure would be gamma of water and H. And H is simply this distance. Which is equal to 4 meters, right? All right, and then area of CB. So I'm going to plug in the numbers, 9,810 times H is 4, and area of CB would be 1 meter, which is the width, times, again, radius of the quadrant, which is 2 meters. So when you calculate F, it would be equal to, I need to take a look at my notes, 78.5 kilonewton. All right, that is F. And remember, F is the force due to pressure on CB. The next thing that we need to calculate is W. W is the weight on top of the curve AB. Basically, the weight of the water on top of the quadrant, right? It's really easy to calculate. You just need to know the gamma of water times volume of ABC. Gamma of water is 9,810. Volume of ABC would be area of ABC times width, which is 1 meters into the paper. So area of ABC, it's a quadrant. It would be 1/4 of area of a circle times 1 meter into the paper, the width of it, right? So if you put R as 2 meters, then W would be equal to 30.8 kilonewton. Perfect. Now I can simply continue and writing this as 78.5 kilonewton plus W was 30.8, sorry. 30.8 kilonewton. The result would be 109.3 kilonewton. All right, so what we did, we calculated FV, vertical force, and horizontal force, right? This was the method that your book used to calculate forces. Now, I'm going to move to next slide and show you how to calculate the location that these two forces act on. According to calculated values of FH and FV, you can write down the equation for the resultant force and simply calculate the resultant force based on these two values. If you do that, it would be 146.9 kilonewton. All right. Now we are looking for the location that this resultant force acts on, and that would be the center of pressure, right? So let me actually sketch our gates once more. So this is point B and this is point A. This is point C. So if I consider this as my center of pressure, I still don't know the location of it, just random one. This would be horizontal force, and this would be vertical force, and this is FR, resultant force. Sometimes you are asked to find this theta. And this theta is really easy to find. Why? Because when you have the value of vertical and horizontal, then tangent of theta is equal to F sub V divided by F sub H. And then in our case, this value is equal to 1.11. So then you can use your calculator to find theta, which would be 48 degrees. Okay? Sometimes you are asked to find theta. But right now, we want to find the exact location of CP, or center of pressure. In other words, we want to find this Y, and also we want to find this X. So what we are going to do is to find the depth and the width to center of pressure. So I'm going to start with the horizontal force. For the horizontal force, you would calculate YP to be equal to Y bar plus I bar, Y bar times area. And this area is vertically projected area, right? And because we have the vertically projected area is vertical, then Y bar is equal to H bar. So I can simplify this equation and write I bar can be found from figure A1, appendix 1 of your book. And we already found H bar, right? H bar was 5. I'm not going to write the units to save some space, but when you do it, write the unit for consistency. Plus, again, 5 times area. We are talking about the vertically projected area that FH acts on, right? So it would be 2 times 1. This number is basically this, which is 2 meters, and then 1 meters into the paper. Now, the only thing that I need to write is I bar, and I bar is, if you take a look at the figure, for a rectangular area, I already know that by heart. recommend you know that for a rectangular area by heart too. So it would be 112 times 1 times b, or in this case our b is 2 meters. 2 meters to the power 3. All right, if you calculate this value, it would be equal to 5.067 meters. Now, what is the physical representation of that? This value is equal to over here. So this purple line is your YP, right? Cool. Now, what would be our Y over here? This is our Y, right? From point C to the center of pressure. So if I want to calculate Y, it would simply be, I'm going to write it with green, Y would be YP minus 4 meters, this 4 meters over here. So it would be 1.067 meters. Now, I found Y, now I need to find X. So X is related to the vertical force. In order to find X, you need to, based on the method that your book has done it, you need to write the moment equilibrium. All right, what does that mean? So we are going to write down the moment equilibrium about point C. It would be pretty easy actually. So what are the forces that act on that? So let me show you. W, F is here, and then the total force is FV, right? So F is the force due to the pressure over here on surface CB, and it acts right at the midpoint, right? So I am going to write down the moment that vertical force generates is equal to force FV times X. And we're talking about this X over here, right? In order to make it clear, let me the moment that the vertical force generates is equal to F of vertical times X. And we are talking about this X over here, right? We are writing the moment equilibrium about point C. Now, other forces is W and F. The moment that W generates is weight times this distance over here. This distance that I'm showing over here, right? What would be that distance? Again, you need to go to figure A1 and find that distance. You will basically, if you go back to your book, you will find out the centroid of a quarter circle, a quadrant over here, and then you will be able to find this distance over here, right? That would be, if you go back to your book, you'll find that that number is 4/3 radius of the quarter circle divided by pi. The moment that vertical force generates is equal to the magnitude of vertical force times its distance to point C, which is X. And I'm talking about this X over here. This should be equal to, remember that I'm writing the moment equilibrium, this should be equal to the moment that other forces generate. What are the other forces? F and W. So I'm going to start with W times. The distance from W to point C is this distance. So W is the weight of that volume of quadrant on top of surface AB, right? So if you go to figure A1 of your book, A1, you would see that you can find the centroid of the quadrant. And that distance, you can write it over here, which is 4/3 radius over pi. All right, and then plus another type of force that we have is F. F is the force due to pressure on top of surface CB. So I will write F times the distance from F to point C, which is this distance. All right, remember that pressure is hydrostatic on surface CB, so that distance would be basically right at the midpoint because we have 2 meters over here. Then the distance from force F to point C is simply 1 meters. All right, now you need to put the radius over here, which is 2 meters. And then we already calculated the values for W and F. So you just plug in everything. You already calculated the W for FV over here. You just plug it in over here. The only unknown variable is X. So based on this equation, you'll find X to be 0.957. Okay. So now you have the value for Y and you have the value for X over here. And this is how you can pinpoint and locate the location that FR, or resultant force, acts on. Now that you learned the method that your textbook uses, I'm going to teach you another method that I personally think it's easier to understand. It's more intuitive. So personally, when I solve any problem in fluid mechanics, I use this method because it's easier. It's based on the weight of the column of water. So first of all, let me make it clear that FH, horizontal force, and YP are calculated exactly the same way that they were calculated in method 1. The difference in method 2 stems from vertical force. So in order to calculate the vertical force, you only need to calculate the weight of the column of water above your curved surface. In our case is AB, right? So in order to calculate weight, you can calculate weights based on, so another equation for weights is gamma, or specific weight, times volume, right? So I can write down that FV is equal to gamma of water times volume of, so I'm going to calculate this volume that I have shown over here, but I'm going to basically split it up into 2 volumes. The first volume would be the volume of the quadrant, or volume of A, B, C, right? And the second volume is going to be the volume that is represented by C, B, D, E. Okay? So to do that, I'm going to write it over here. Gamma is 9,810 Newton divided by cubic meters times. Volume would be area of ABC times its width. So area of this red polygon that I'm showing it to you times its width, which is 1 meter. So I'm going to write it over here. Area would be 1/4 of pi times radius is 2 meters to the power 2 times width is 1 meter. Now, plus, again, 9,810 Newton divided by cubic meters times volume of CBDE. That's easy to calculate too. It would be area of this rectangle times width, which is 1 meter. So again, it would be, I'm going to write it with red, the area would be 2 meters times 4 times 1. There we go. Now if you calculate this, you would see that again, FV would be 109.3 kilonewton. And this is exactly what you found based on the previous method that your textbook suggests. So as you can see, this method is a little bit easier because you do not need to calculate F separately and W separately, right? You just calculate the weight of column of water above AB. Now you might ask, then how do we calculate the location? The location that FV is basically exerted on or acts on. Now let's move to the next slide to talk about location. Finding the location is easy as well. How do we find it? So this is the geometric shape that we need to find centroid for. Because this is a weird shape, we need to break it down into two shapes that we are familiar with. So I'm going to break this down into one rectangle, this one, and then another one would be a quadrant, this quadrant. Now I can go to the back of the book and find centroid for a rectangle and for a quadrant. For a rectangle, I know that the centroid would be in the midpoint, right over here, right? So if that's in the midpoint, this value is going to be equal to 1 meter. 2 divided by 2 would be 1 meter, right? I'm going to call this x of the rectangle, xr. Now, how about for the quadrant? For quadrant, again, if you go to figure A1, you would see that this distance is equal to, I'm going to call it xq. X for the quadrant would be 4 divided by 3 radius divided by pi. And that's the x for the centroid of the quadrant, okay? So also you can find the area of these two as well. So area of rectangle is equal to 2 meters wide times 4 meters length would be 8. And area of this quadrant would be 1/4 pi 2 to the power 2. Okay, so now the only thing that you need to do is to find out the weighted average of these. Weighted average of these will give you the value for x. And remember, what was x? X was, if this is this is FR, this value was your x, remember? Okay, so to find x, you just need to take the weighted average of these. Weighted average means you have xr times AR plus xq times AQ divided by AR plus AQ. So if you calculate all of this, again, your x would be equal to what you calculated in previous method. If I take a look at my notes, it would be equal to 0.957 meters. So these are the two methods that you can calculate different parameters when it comes to calculating forces and location of hydrostatic force.